Welcome once again to a tutorial on the BJT operational modes, and as you can see, well, here's where we continue from where we started back in the previous tutorial. Okay, so in the last tutorial we discussed about the common base or the CB mode, and now in this particular tutorial we're basically gonna start with the CE mode of operation. So here goes. So here we're just gonna study about the common emitter mode. Okay, so I'm just going to write it down over here. Let's say common emitter mode. Okay, also referred to as a CE mode in short. Alright, so there you go. Now as you can see in these two diagrams over here that, well, we are having the two types of BJTs. So one's the NPN, okay, and on the right we have the PNP type of BJT over here. Now both of them in the CE mode of operation. So you can well see over here that, well, as you'll know, that the common emitter mode obviously stands for that mode of operation where we just have to ground the emitter terminal of the BJT concerned. So what we have done over here, that we've just connected the emitter terminals of both the types of BJTs to ground, as you can see over here. Okay, and well, the power supply sources are present in both the input and the output loops of both the two diagrams that we've just provided over here with their corresponding polarities concerned. Okay, and the polarities have been such in order to, well, forward bias the base emitter junction in both the types of these circuits, okay, and also to reverse bias the collector base junction in both the types of circuits that we have seen, we just provided over here. Okay, so if you all would just try and see that, well, the PNP type of BJT in the CE mode of operation is little, difficult to, well, conceive and, well, visualize and all. So what we'll be doing over here is that we'll just take the NPN type BJT as a reference for studying the internal mechanisms over here. So in order to go forward, we just gonna go and, well, study about the input characteristics first. So there we go. So here we'll study first the input characteristics. Okay, so I'm just gonna write it down over here. Alright, so in order to study the input characteristics, we'll need to, well, modify one of the figures over here to set up the experimental arrangement. And let me just tell you, in this particular, the studying the input characteristics, we're basically gonna, well, yeah, you're right. We're basically gonna study the input current versus the input voltage curve. So that's exactly the base current versus the base emitter voltage curve. So if you'll just take a look once again at these two diagrams, you can see, well, here we have the base current as the input current to both the BJTs, since we're having the base terminal well, used as the input terminal in both the cases, since the emitter terminal over here is used, connected to ground. So this is just contrary to what we saw in the common base mode, where the emitter terminal was just used as the input terminal to both the BJTs. Okay, so now well, similar to the common base mode, that's the CB mode previously that you've seen over there, the collector terminal over here serves as the output terminal, and quite usually the output current, that is going to be well, obtained at the collector terminal itself. So there you go. Yeah, I'll just write IC over here, and, well, we'll have the emitter current just, well, going out through the emitter terminal. Okay, so these are the directions of the current in case of the NPN type of BJT concerned, and now for the PNP type BJT it's just the reverse. So here we're gonna have the base current directed somewhat this way, okay, and then we'll have the emitter current going upwards, okay, from the emitter towards the collector, and finally we'll have the collector current just coming out of the collector terminal. So these are the directions concerned in both the NPN and PNP type of BJTs concerned. Alright, so in order to just go forward into the input characteristics, we're just gonna need an experimental setup. So okay, so let's just bring up the experimental setup over here. Okay, so there's the diagram concerned for our experimental setup using an NPN type of BJT. Okay, so as you can see over here, we are gonna keep the V1, that's the voltage source, connected at the input loop over here. Okay, we are just gonna connect or rather just keep this V1 over here as a variable voltage source. Okay, so just gonna keep it variable so that we can just, well, vary the amount of input base current. So here the base current, that's IB, would be kept variable as well. And similarly, if we just, well, vary the magnitude of this input supply voltage over here, then we're also going to vary the amount of forward bias voltage falling on the emitter junction over here, rather the base emitter forward bias voltage. So here we're also going to keep, or rather this base emitter voltage would also be kept variable, so that we're just gonna, well, study this sort of graph over here. All right, and over here at the output loop, if you just take a look over here, that in the case of the output loop, we're just going to keep V2, that's the supply voltage, or rather the bias voltage for the collector junction over here, that's V2. We're just going to keep it constant. We're not going to, well, vary this one. So under this sort of a setup, if we would just take various values of study the variation of this input base current with varying values of the base emitter forward bias voltage, then we're gonna basically get a graph that would look something like this. There you go. There we have our graph of the IB versus VBE curve. So as you can see, well, we're gonna basically, well, we are just having the red line, indicating the nature of variation of the input base current with respect to the base emitter forward bias voltage. Okay, so as you can see, well, here we're just getting a curve that's, well, physically similar to the forward bias characteristics of a PN junction diode. Okay, and, well, in contrast to the previous tutorial on the CB mode, we're just taking the base current as the input current for this particular configuration of operation of the BJT. So in this one, you can see, well, if you just refer to the circuit diagram once more, that the base current, as you all know, would be quite a small amount of current, because it's just the result of recombination while the carriers travel from the emitter towards the collector terminal. So as a result, what we're basically going to have is that we're going to have very short magnitude of base current. Okay, it's going to be very, very little in magnitude. So we've just included a milli emitter over here, just between that of the base and the supply voltage terminals. That's as you can see right over here. There you go. So this milli emitter obviously indicates, or rather records the current in in terms of milliamperes. Okay, so it's quite small, as you can see, but the nature of this curve over here would remain the same as that of what we saw in the previous tutorial, similar to the diode forward bias characteristics, because of the nature of variation of the emitter current. The base current is obviously directly proportional to the emitter current. More emitter current, meaning more the recombination, and hence more base current. So that's why you can see that on increasing the forward bias over here, the amount of base current obviously increases, similar to the type of increase seen in the case of the emitter current. Okay, so this is what we have in case of the input characteristics. But now if we just care to, well, modify this setup a little bit, so that we can just, well, make V2 variable right over here. So I'm just going to write that down. So if we just make okay, so that's better. If we just make V2 variable also, then we need to obviously include this sort of symbol. Okay, and also we need to connect a voltmeter VB across the collector and emitter terminals, as you can see over here. So now if we would just care to well, note an effect of the variation of V2 in on the the input curve over here, then you can probably see that the curves in this particular figure over here. So notice the change that, well, takes place, that we previously had the red curve only that represented the variation of the base current and versus the base emitter voltage. Okay, where the VCE, that's the collector emitter voltage, given by this, the source voltage V2 that's connected across the collector emitter terminals, that is supposed to, well, reverse bias the collector junction over here in this BJT. So the voltage, the voltage, coming from the voltage source V2, well, if we just increase that to about, let's say, 2 volts, or rather previously if we just keep it to 0 volts, so this is the sort of variation represented by the red curve over here. But whenever we just increase the voltage on that particular voltage source V2, then as VCE increases, we can see that the curve just slants more towards the right. Okay, so this is probably due to the reason that of the base with modulation, or the early effect, as you can see over here, is because more the reverse bias voltage on the collector junction increases, it just reduces the base width even more. So with base width reduced, obviously the base current would just decrease. So IB would decrease on a reduction of the base width. So that is what basically leads to a little, or rather a reduced amount of base current over here, due to lower amount of recombination produced when base becomes thinner. And that's why with each given rise in the forward bias voltage, the curves do not rise as sharply as before. So that's the reason over here. So we're also going to get the same sort of a curve if we would just employ a PNP transistor in place of an NPN transistor for the experimental setup circuit. There it is. That's the experimental setup circuit for the PNP type of BJT. So it's just quite similar in resemblance of the NPN and the PNP type BJTs, but only the voltage polarities are just different. Okay, so now that we have just known about the input characteristics, now we can just quickly just move on to the output characteristics in order to study what happens in the output loop. So over here, we're just going to study the output characteristics of the BJTs. Okay, so I'm just going to write it down over here. Okay, there we go. So in the output characteristics, basically what we're going to study is, we're just going to study the variation of the collector current versus that of the collector emitter voltage. Okay, so we're just going to study the variation of these two parameters over there. Okay, so now by just reverse biasing the collector junction using the voltage source V2 over here that we have just connected across the collector and the emitter terminals, we just set up a voltage difference between the collector and the emitter terminals, which we just call okay, I'll just write over here, which we just call VCE. Okay, so that's a little bit of cramping up over here. I'll just redraw the diagram once again so that it does quite remove the the voltmeter a little further so that it's better and clearer to see. Okay, so just kind of hold on for a second. There you go. And now this obviously sets up a voltage difference of, known as, VCE. That's the collector emitter voltage. And here the amount of reverse bias voltage that's just produced across the the collector junction is just represented with the VCE. That's the collector to emitter bias voltage. Okay, so now basically by keeping V2 variable, so we just got to keep V2 variable over here, and that is quite mandatory. Okay, so just by keeping V2 variable, we also keep VCE a variable in this case. That's the the reverse bias voltage acting across the collector junction. Okay, and apart from that, we also need to measure the amount of collector current that just comes from the voltage source V2 and enters into the NPN type BJT. Okay, so that's why we just included an emitter over here in order to measure the amount of collector current. Okay, so so in order to just keeping V2 variable, VC is variable, so is the collector current IC. Okay, so that just will facilitate our studying of the variation of the collector current versus the the collector emitter bias voltage. So just keeping V1 constant for this particular moment, we need to use a variable voltage source in case of V1, basically for the reason that we'll be needing to studying the variation of the collector characteristics, or rather the output characteristics with reference to the input base current. Okay, so that's for the later purpose. So we just for this moment we just keep V1 as a constant voltage, okay? And then if we just perform the experiment over here, then we're gonna get a graph that would look something like this particular curve, as you can see over here. So in this curve, it shows that, well, for a particular value of for a particular fixed value of the input base current, that's IB equals to about, let's say, 0.3 milliamps, okay, we just obtain this particular curve as denoted with this red line, as you can see. So over here you can see that, well, as we go on reverse biasing the collector junction with the help of the collector emitter bias voltage, we can just see that the collector current basically rises till a certain extent, and then it just begins to, well, it doesn't rise that rapidly anymore. And as soon as it enters into this particular region over here where the curve is almost flat, but there is a certain increase with larger amounts of bias voltages, so that is due to obviously the early effect. We'll discuss about it, but if we would just care to, well, investigate the curves for different amounts of the base currents, so in that case we'll need to obviously, well, make IB a variable as well as a V1. Okay, so I'm just going to write that down over here. So we're just making V1 and hence IB variable, so that for different values of IB we can get to study different values, different types of output curves. So that just leads us to the point where we'll basically find that. There you go. So we are gonna, supposed to get something like this, as you can see in this particular graph over here. So for different values of the base current, that's the input current for this particular mode of operation of the BJT, we're gonna get the different curves, as you can see, for different values of IB. So with the first one starting from, well, when IB is equals to 0 milliamps. So if we need to keep IB 0, then if we just take a look at the circuit, then we'll obviously need to keep the base emitter terminal reverse biased. So under the condition of the base emitter terminal, the base emitter voltage being reverse biased, we'll obviously need to reverse the emitter junction as such. So the emitter junction remaining reverse biased, and so does the collector junction, we'll get this particular region, which I'm just going to shade in white. There you go. So we're just going to get this particular region of the curve where the base current, that's the input current, would be almost 0 milliamps, and obviously that would just lead us to a collector current of nothing more than the ICO. That's the reverse saturation current that's just available in a reversed biased collector junction. Okay, so under this particular scenario, keeping the emitter as well as the collector junction reverse biased, we're just going to get this particular region over here, which is just termed as the cutoff region. Okay, so that's we're just going to study the graph in detail based on these three regions, as we'd seen in the previous tutorial. And apart from that, we also have this particular region where the collector current just rises with the increasing reverse bias voltage. Okay, so you can see that it's very close to the 0 mark over here, and that is this portion is obviously demarcated with the yellow dotted line. So this particular portion over here represents the saturation region. Okay. And let me just tell you that in the saturation region, the emitter as well as the emitter as well as the collector junction is obviously, both are just forward biased by a little bit. So it's not that we just put a full-on forward bias at the collector junction as such. It's just not like that. It's like we're just not applying any sort of reverse bias. We may just keep the collector junction at 0 volts, or maybe a little higher than 0 volts, like 0.25 or 0.3 or something like that. So with little forward biasing, or rather the collector junction kept at 0 volts even, we are supposed to get the saturation region. So we just begin to reverse bias the collector junction from here on. And after we've just reverse biased the collector junction and the emitter junction being forward biased on the other end, we get this particular region that you can see where the curves just begin to stabilize and become parallel to each other. So this particular region over here represents the active region of operation. Okay, but there's a slight difference between the active region in a CB mode and the CE mode of BJT operation. The fact is that, well, in this case you can see that the curves, well, are not exactly, well, horizontal, although they are parallel to each other, but they're just not horizontal. They suffer a little a little increase upon, for higher values of reverse bias voltage. That is obviously indicative of the fact that the early effect, well, reigns higher in this particular mode of operation. So in this case, what happens is that due to early effect, the the base width, as it just gets smaller and smaller, the collector current would obviously rise due to higher amounts of emitter carriers just crossing over the base section of the BJT. So that just leads us to this particular phenomena where the curves just tend to rise their raise their ends as such with higher amounts of reverse bias voltage across them. Okay, so that discussed, we can also view the curves for a PNP type transistor. There you go, and there's the setup for the PNP type of transistor. So here's the graph, which looks almost quite similar to what we saw in the case of the NPN counterpart of the BJT. And here's the setup. So if you just examine the curves once more closely for both the PNP and the NPN types, you can easily see that for a little amount of base current that acts as the input, we're getting lots of collector current. So over here we can just state that, well, the collector current is equal to some constant multiplied with the base current. So whatever the base current is, it's about a multiple of the collector current. So if you just take any random values from over here, let's say just take, well, we can just see that for about 0.3 milliamps of base current, we're going to get about, let's say, 30 milliamps of collector current. So if you just divide that, then we can get, well, let's say 30 milliamps over here of collector current. That's IC, and that we're just dividing it by the 0.3 milliamps of base current. So there you go, that's IC by IB, and here we can get as equals to about 100. So we can see that this K factor, which is of course defined as the multiplication factor over here, so I'm just going to write it down over here, that's the multiplication factor, obviously multiplies the base current by 100 times to produce the collector current. So we can just write it down over here in some other color. Yeah, I'll just take yellow. So we can say that, well, IC is about equals to, well, beta times that of IB. So where beta is of course the multiplication factor. Okay, so there you go, that's the multiplication factor over here. And now this particular factor, well, multiplies the base current 100 times to produce the requisite amount of collector current. And now it is for this particular value of beta, which is also defined as the it's also defined as the current gain for this particular type of transistor operation or mode. Okay, so it's for this particular higher values of beta in the common emitter mode that we can see this particular mode is perfectly suitable for operating the transistor, or rather the BJT, as an amplifier type of operation. Okay, so that said, we just come to the end of this tutorial video where you've just come to learn about the CE mode of operation of the BJT. So see you back in the other tutorials on the BJTs, and don't forget to catch them. So it's just going to be a short goodbye for now, and thanks for watching.